So we're going to start. And Todd, let me tell you briefly about the audience. We have here several professors from the department. We have, I saw Dr. Peter Antematin, who is the chair over there. We have Dr. Fred Chambers, Dr. Ben Crawford, Dr. Alicia Coward, and Dr. Gary Salmon, Director of Grad Studies. Who else am I missing? Faculty. Brian Weed, Dr. Brian Weed there at the top, and Kathy Kelsey, also one of our physical geographers over there. So, and then we have the brilliant students right over here. We have, if you could please raise your hand, those in the Masters of Science of Environmental Science, Master of Science in Environmental Science. And then we have the students in the Masters, um, Master of Arts in Applied Geography and Geospatial Science. And if you could raise your hand, please, guys. Awesome. So perfect. Also, Dr. Thomas Duster over there is our another one of the faculty. All right, so let's get started. I will do a brief presentation of Dr. Todd Brewer and a little bit of his background. I have asked him to not be humble and compliment a little bit about what I will say, because it's important to hear about the path. It's something I think it's a good thing for us to hear. And for many students, you could say, I could do that, right? All right, so also Dr. Lisa Kelly just joined us. Perfect. So Dr. Brewer is currently the Senior Manager of Grants, Education, and Utility Programs with the American Water Works Association here in Denver. He's also the Senior Manager for Partnership Programs at the AWWA, the American Water Works Association, and also oversees the continuous improvement and optimization of programs for drinking water treatment, drinking water distribution systems, and water treatment facilities. So he has more than 25 years experience in the drinking water utility field and has licenses as a water operator. And I think he will tell us about the big deal that is as a water operator in both Oklahoma and Missouri. He's also a licensed professional engineer and holds a PhD in environmental engineering from the University of Nevada, Reno. On top of that, he also teaches college-level chemistry and engineering courses for the last 22 years and workshops for the AWWA. And last but not least, he's the proud father of two of our amazing grad students, Haley and Sarah. So awesome. So as you can see, is a fantastic guest speaker. We're looking forward to your presentation, Todd, and you can take it away.
Well, thank you, sir, for the kind introduction. I appreciate that so much. Let's see here if I can get us started off right. And can you see my PowerPoint screen there?
Yes.
It would be bad to kick off a talk about technology advancements and I can't even share my screen appropriately, but sadly that's the case some of the time. So again, thank you all so much for having me today. I am the proud father of two of your students in the program. They always keep me on my toes, and I expect no less today as well. So Raphael and I have had a chance to talk a little bit over the past few months about the colloquium and about kind of the breadth of my experience. So, we'll talk a little bit more about me than I normally would, but I do think it's important, as he referred to, is, this isn't exactly what I envisioned for myself starting out, but I couldn't be happier about where I've ended up. I didn't even start out planning on being an engineer. To this day, I really consider myself a scientist, proudly. I'm proud of being an engineer, but science to me is such a noble endeavor, and more so than a discipline, it's really kind of a commitment to a way of thinking. Right? As we learn more, we revise our opinion based on the facts and evidence, and a commitment to that. And I'm a big Carl Sagan fan and his philosophies on how to approach life in the scientific method. So that's a little bit about me. We'll talk more about kind of my path that brought me to where I'm at today with AWWA. Hopefully some of that resonates with you all too, because I didn't have it all figured out in the beginning, and more folks than not probably are in that same spot. So we'll talk about continuous improvement programs, certainly public health protection, which is at the very core of what drinking water protection or treatment is all about. Water resources management is a big part of effective drinking water treatment, public health protection through the provision of safe drinking water. And then certainly what's probably of most interest to you all, maybe not, but probably the role of GIS or GIScience and Technology. So a disclaimer, I'm not an expert in that area, but one of the things that I've seen certainly over the last, I'll say 15 years or so of my career as a water quality manager and a researcher, both in natural waters and in treated and finished waters, is the nearly limitless potential of the application of this field to turn data into information. And, at the forefront of public health protection, you think about what's happened in Texas, or 100-year or 500-year flood events, tornadoes, natural catastrophes, hurricanes on the East Coast or in the Gulf Coast. The ability to turn data points into information so that we can make decisions quickly in support of the relentless protection of public health is an absolutely critical tool to have and a skill set. So I'm not an expert in it, but I certainly recognize that it's extremely valuable and even more valuable than I recognize. So we've already talked a little bit about me, and we'll weave more of that and my journey into the conversation as we wind through the hour or so of my presentation, and I look forward to having a discussion and a dialogue at the end of all of this too. So we'll talk a little bit about AWWA, the American Water Works Association, the continuous improvement and optimization programs that I manage, the original reason that I came to AWWA. And of course, we're going to talk towards the latter portion of the presentation about the importance of GIS within kind of, the areas that I work most routinely. So the American Water Works Association, waterworks are just that, they're public utilities. It is the American Water Works Association, or as you'll hear me call it time and time again, AWWA, is the world's largest water association. And currently we have a little bit more than 50,000 members, mostly folks at utilities. There are a lot of folks in academia that are part of the association as well, consulting engineers that lend their expertise to solving problems, whether it's treatment related issues or infrastructure renewal challenges. So we have, and we even have, regulatory folks that are part of this association as well, whether they're, at the city or metropolitan level, they're at a county or state or even federal EPA. So there are a lot of folks that are invested in the protection of public health. Our primary membership is in the United States, but we actually have members throughout the world. The number of countries, I should know that, but there's several dozen countries that we have membership in. A lot of folks in Canada and Mexico, Australia, and throughout Europe, we have membership in the American Water Works Association. I guess we're becoming much more international and worldwide in recent years. So, that's a little bit about the background, the history of AWWA. This is the 140th year of existence of AWWA. So founded in 1881, just recognized our 140th anniversary, but it is, like I mentioned, the largest organization of water supply professionals in the world. And there's a huge library and universe of education, technical resources, management resources, all kinds of good stuff for folks that are in the business of protecting the environment and providing safe drinking water. There are all sorts of things there, and maybe almost as important as the technical resources is the network and community of like-minded folks that hold that mission of protecting public health in such high regard. So, I talked about the scientific method, and as we learn more, we revise our opinion. And certainly the things that we knew about safe drinking water in 1881 have changed an awful lot. Certainly the things that we knew about safe drinking water in 1981 or 1991 have changed quite a bit in the last 20 or 30 years. And a lot of the things that you all are studying in pursuit, of your master's or higher degrees have absolutely helped us take kind of a quantum leap forward from the data collection phase to turning that into information. So there's a lot of, to me, great stuff going on at AWWA, and it's really a community of lifelong learners in pursuit of that, to me, that ideal of trying to provide safe drinking water to as many folks, in the world as we possibly can. There's an avenue. I'm not here to sell you on AWWA membership or anything. I do talk to my girls about it, but one of the things that most areas, career areas in the United States are faced with as a challenge is there are more folks that are able to retire and to move on to the next phase of their lives than we have coming into that area. There's the brain drain or the silver tsunami or any number of other things that they might refer to it as, but we've got more folks that are deciding to chase grandkids around full time or vacation and are retiring out of the industry. So that's a problem. Certainly we want to be replacing those folks with people that are just as committed to protecting public health and learning, relentlessly to that end. So one of the things that AWWA has been doing for several years is trying to make it really easy for young professionals and for students to join. I think one of the things you might see there in the water drop in the lower right is it only costs about $10 a year for a student to be part of AWWA. A lot of the resources that are out there, access to some of the stuff about the programs that I manage that I'll talk about here in a little bit in more detail. YP activities, the Young Professionals Summit every year. And not only are they trying to broaden the horizons of the folks that may have interest in pursuing a career in water or wastewater, they're trying to link them up with people and give them a network. The YP Summit is held every year nationally in conjunction with the Utility Management Conference. So that's a lot of the higher level folks from Aurora Water, Denver Water, and Metropolitan Water District of Southern California, and utilities all across the country have those folks that are looking for the talent to come in and help take them, into the future foreseeably in providing safe water with their utility to their communities. Career Center, networking, opportunities for presenting research at different section and national conferences, and just getting kind of plugged into what's going on there. There's a lot of benefits for $10 a year, access to all sorts of different publications out there. So just another avenue for you all to investigate what may catch your fancy and what you want to do after grad school. So I want to talk just a little bit about how water works. And this, hopefully I'm not backing up too much here, but to kind of put into context, how critical what you all are studying and mastering there is to our efforts in water and wastewater. I want to talk just a little bit about the multiple barrier concept and really this kind of overview of how water works really from source to tap and back again. So, on the Front Range, we see that water makes several stops on its journey from the source to someone's tap and being used. And then of course it goes down the drain and it goes back ultimately through wastewater treatment and back out into the natural environment. So, here along the Front Range, and I think there's a slide here and just a little bit further downstream in our presentation that talks specifically about some of our water budget. But we have about 80 to 90% of our population in Colorado on the Front Range on the east side of the mountains, and probably a full 80% or more of our water resources tend to flow to the west. So that's obviously an issue. That creates a lot of challenges. It sure creates a lot of need for folks that are in our respective areas. But what we see, even in a mountain watershed, is that there are several stops along the way. We may have a drinking water treatment facility. If you were to picture something maybe kind of more in the Midwest along the Mississippi River, there are thousands of communities that use the Mississippi River water resources, either for farming, for a drinking water source. And so when you look at the headwaters somewhere up in Minnesota to all the way down where it dumps into the Gulf of Mexico near New Orleans, that water's been used, treated, reused probably thousands of times. So there's certainly a public health aspect. There's an environmental stewardship aspect. And, when a drinking water facility is treating its water, there's a very, very small percentage of that water that actually is used for potable purposes, such as drinking, cooking, making tea or coffee, any of that sort of thing. It's less than 5%. On average, it's maybe 1 to 2% of that water that actually is going for potable use. So out of every 100 gallons, somewhere between 1 and 5 gallons of that is actually, touching food or being used to make some sort of something that somebody's going to ingest. The overwhelming majority of it is for things like washing clothes, taking showers, maybe watering lawns in some parts of the country, non-potable use, but the whole 100% of it needs to be treated for, the provision of safe drinking water. So that's a challenge in itself. And certainly at times we have some conflict between the goals for the provision of safe drinking water, say something like corrosion control, where maybe a phosphate corrosion inhibitor may be the best choice for protecting the deterioration of the distribution lines that deliver the water. But for the wastewater facility, that's a problem to have phosphorus in there, because that's a limiting nutrient out in the environment. It's a problem for them to remove for discharge. So what is good for the drinking water end of things creates some challenges and some expense and hardship really on the wastewater end of things. And certainly we want to be protective about excess phosphorus out in the system. That's where we can get into harmful algal blooms and eutrophic states in natural waters. So there's a lot of things going on, and it's complex. But and all of that against the backdrop, even though there's only somewhere between 1 and 5% of the total water that a drinking water plant would produce on a daily basis being used for potable purposes. Just ask yourselves right now, it's 3:30, 4 o'clock in the afternoon. If you had to guess how many times you've used tap water today, could you get close? My guess is most of you would underestimate. Most folks do, even though it may not be a bunch of water at one time between brushing your teeth or, making some breakfast or some tea or some coffee or washing your hands or all of those things. It certainly is used far more often than most folks realize, because it's largely in the US, you can count on the water to be there when you turn the tap on. And that is not the case in a good part of the rest of the world. And I meant to give you a statistic there when we talk about the importance of the provision of safe drinking water. And I got sidetracked as I was looking at kind of the, a day in the life of a drop of water diagram there. But each year annually, according to the World Health Organization, there's an estimated 2 million deaths worldwide related to waterborne disease. About 90% of those deaths are children under the age of 5. Things like cholera and dysentery, typhoid, things of that nature. And most of you in attendance today would probably be pretty hard pressed to name the most recent or the biggest waterborne disease outbreak that you've heard about in the United States, or even besides a waterborne disease outbreak, a water quality issue that impacted the health of the community. Certainly Flint, Michigan is one that everybody's heard about, most everybody's heard about over the last few years. But in terms of a waterborne disease outbreak, that's part of, how effectively we apply the multiple barrier treatment concept in the US. And I'll talk about that here in a few slides. So I mentioned just a few minutes ago that about 90%, of our water is drawn from the snowpack in the Rocky Mountains. But as far as our water resources go, like I said, all the folks are on this side of the mountain, and Mother Nature and gravity take most of our natural rainfall to the west. And that creates some water resource issues and constraints, certainly here in the Front Range. So how does water work? And we've got a diagram in a minute to talk about the multiple barrier treatment concept. But water treatment systems in the US and in the developed world are designed to produce a very high quality of drinking water. What you see here in this diagram from a raw water in the business is an untreated water. It could be river water, it could be lake water, but it's something that certainly a surface water, it would be expected to have bacteria, viral contaminants, but it also would be subject to contamination from surface runoff. If it's in and around a city, there's any number of things. It could be runoff from roadways and impervious surfaces, vehicle fluids, things of that nature. More rural areas, it might be impacted by agriculture or septic systems that aren't functioning the way that they were designed. And just simply runoff with, soil and sedimentation and turbidity and things of that nature. Wildlife and their waste streams. So there's stuff in that water that needs to be removed in order for it to be safe for drinking. So coagulation and flocculation are key to effective filtration practices. If we were to take a mud puddle after a good rain, and we were to scoop it up in a pitcher, a clear pitcher, and we would just let it set on a table for an hour, and we were to come back, we'd see that down in the bottom of that pitcher is a pretty noticeable layer of silt. And this is the big stuff. This is what's going to settle out naturally without any help from us. That sort of sedimentation is one of the reasons that rivers form meanders. As you go around curves, you'll have deposition of these larger particles, and over time, it changes the path of the river. But there would also, that water would still be pretty dingy. It'd be cloudy. If you were to hold it up to the light, you could see floaties in there. And there are going to be some smaller and smaller particles that would just never settle out. They certainly wouldn't settle out in a time frame that lends itself to providing drinking water to a community, certainly to millions of people. That's where coagulation comes in, and you get into the science of that, but we can add chemicals in there that minimize the repulsive forces of these small particles. The flocculation is the gentle mixing energy that we provide to promote collision, so the little stuff clumps into big enough stuff to want to settle out, sedimentation. So those three processes are really designed to remove as much of that stuff as we can prior to going through the filters. So the cleaner the water that we can put on the filters, the longer the filters operate before they start to clog up and we have to backwash them. Disinfection is key. One of the reasons it's so important for us to remove turbidity, this cloudiness, which is really particulate matter in the water, and we'll talk about it again in a slide or two, is that on the surface of each one of those particles, some of them may only be 5 or 10 microns in size, but that's a surface for bacteria and for virus to attach to. Now, we can't on the fly measure the amount of virus coming out of the treatment plant or the amount of bacteria. We can measure pretty routinely, but not in real time. But we can very effectively measure the particulate matter and the turbidity. So it is a real-time surrogate for how well we're clarifying the water. And the more dirt and stuff we remove, the more bacteria and virus and microbial contaminants that can cause public health issues are being removed. And then we try to disinfect later in the process. Now that we've removed a lot of the interfering contaminants or substances, now we can disinfect, and a much larger percentage of the disinfectant goes to inactivating microorganisms and virus, as opposed to being soaked up by the dirt and other stuff that's in there. So this is all kind of part of this multiple barrier treatment concept. They're all critical. And, in the interest of time, I want to give you a flyover so we can spend more time talking about GIS. But what sort of professions, what sort of skills really lend themselves to being in this industry? A big, wide range. Operators could have, they don't even really necessarily have to have a technical background. It certainly helps, but if they don't know chemistry and biology, but they have a mechanical aptitude, there's a place for somebody to be an operator, because that's part of what they do too, is inspecting pumps and pipes and valves and a lot of that if that stuff doesn't work, then the water treatment process doesn't work either. Maintenance engineers, design engineers, laboratory technicians, and then certainly planners and schedulers. Anytime that we have large projects, whether it's a large pipe replacement project or a treatment plant capital improvement project, that isn't something that you just decide to roll up your sleeves and get busy next week. It needs to be planned over time so that the appropriate people are brought in during the right phase. There may be plant shutdowns or parts of the system that need to be shut down to facilitate the project. That has to be planned in advance. In some way, it's kind of similar to a roadway project. You can't just shut down a major highway for an indefinite period of time. You need to plan the project to minimize the impact on the operation while you're trying to help it along the way. So I can go through this pretty quickly since I've already talked about it with the diagram previously, but the multiple barrier concept really, for me, and I've been teaching this a while, goes all the way from source water protection. And that's kind of that old saying of an ounce of prevention is worth a pound of cure. If there are practices that we can adopt to keep contaminants from getting into the water in the first place, then that's one less thing that we have to worry about removing for drinking water treatment. Once we get into the plant and the treatment process itself, that's where the coagulation, flocculation, sedimentation, filtration, and disinfection all take place that we were talking about in that previous diagram. But I don't want the distribution practices to be lost in the multiple barrier concept either, because once the water leaves the plant, it could have a very short time and travel through the distribution system to the customer. It might be that it has to go all the way across town, and there could be dozens of miles of distribution main that it travels through before it gets to that end user. Think about all of the other homes, of the industrial facilities, of the businesses, restaurants being that as well. All of those things that are hooked into that system. Construction going on, there can be power outages. There are a lot of things that can go on between when the water enters the system and it gets to that end user that could impact quality. So and this is part of the programs that I manage, having these distribution practices that are all geared towards having as a solid and resilient distribution system as we can, making sure we don't have backflow opportunity in there, or cross connections do not occur. Inspection of the system, all that is an absolutely critical. That's the last mile before folks actually use the water. So this gives you, a really good 5-minute, 10-minute overview of the multiple barrier concept. So why do we need those? Well, I guess I'd say don't put all your eggs in one basket. Any one of these barriers can fail for some reason. We could think about Boulder, Colorado. We could have a 100-year flood, and there can be more turbidity than we would normally have any reason to expect coming into the plant. It's not designed for that. So we can still, through coagulation and flocculation, we can settle a lot of that. We can filter it, we can disinfect. And so we have multiple tools in our box for when life throws curves at us. Also, some of the microorganisms that we're trying to remove, like virus, they're so small that they can pass through filters. So we need to have coagulation and flocculation to catch them and clump them into larger particles. And if somehow, some way, something still passes through all that, we have the disinfection process to inactivate them so that they can't make people sick. Now, the protozoa over at the right are a little bit of a special case in that when we think about those, and I'm not a biologist, but when I used to talk to my engineering students, I'd say, just think like a microscopic turtle or snail. Biologists probably cringe at that explanation, but what I mean by that is when conditions are unfavorable environmentally for them, might be too hot or too cold, or the pH is wrong, or maybe there's a disinfectant present, they have the ability to kind of, in essence, go into their shell and hide from those harsh elements that are in their environment. And then when they're in the right environment, which might be after a person's ingested them and they're down inside a warm-blooded animal, they can come out and become infective again. So they're resistant to disinfection. That's another reason for those protozoa like Giardia and Crypto. It's absolutely critical that we're optimizing coagulation, flocculation, filtration. So we don't want to bank too much on any one of these efforts. We want them all to be working in concert so that we can end up with that best overall water quality. So we talked about turbidity already, the measures of the cloudiness. It's the particulate material in the water. You go, well, a little bit of sand or silt may not hurt anybody, but what about the things that are adsorbed to the surface of that? There are all kinds of microorganisms and pathogenic organisms so the clearer we can make the water, the safer the water is generally for folks to be drinking. That's why we can measure it on the fly very effectively, much more than we can, viral counts or bacteriological counts. Those numbers are always, that's already water that's left the castle walls. And so you're living in the past when you look and do that type of analysis. Turbidity is real time. We talked already about why it's important, because we segue kind of over into the programs that I manage. So these slides, the pictures that you see at the top of the slides here, this is a 0.3 NTU. So the NTU is just a turbidity unit. The higher the number, the dirtier the water. Let me see if I can back up a slide here. Okay, so this water right here on the left would be probably maybe 100 or 200 NTU. That's some pretty muddy water that you might see in a mud puddle or say in a creek after a good rain. And then that looks like treated drinking water, something you might get out of the water fountain or your tap. And that's probably 0.1 NTU or less. So very, very clear water. So you come over here and you see microscopically, this is, even though this water here on that inset of the slide on the top is 0.3 NTU water, it complies with the regulations. Microscopically, you go, whoa, there's still stuff going on in there. But as we go down towards 0.1 NTU or less, comparatively, it's a snapshot, but you see that that's much, much cleaner water. As we start to really look at cyst removal, and I looked for this slide. I'll try to find it and dig it up and send it to you guys. But the point, I wanted to keep this in here even as a blank. As we go below 0.1 NTU, Giardia and Crypto they have the cyst forms. They're in the range of say 2 microns to 10 microns in size. They're very, very small organisms. As we go below 0.1 NTU in water, we see an exponential rise in the log removal. We see much, much higher percentage removals of these cyst forms. So we're not killing them or inactivating them, but we are removing them from the water. So the cleaner the water, the better job we're doing of removing these types of pathogenic organisms. We talked about water distribution. It'll be great for you guys to go back and look at this, but I talked about it already as part of the multiple barrier treatment concept. And it is the last mile. You can do all the good in the world to treat the water, but as all this construction's going on and infrastructure, and you have pipes anywhere from being brand new to, I'm sure that the city of Denver has water pipes in the ground that are more than 100 years old. It's a fact of life in most metropolitan cities. Some of them maybe quite a bit older. You might be shocked to know how old some of the pipes in the ground are. So, just generally, just a high level overview, distribution systems are very, very complex, right? And the way that I typically describe a water treatment plant is kind of like the heart of the city. And then the distribution system, you have these major, like your aorta and these large vessels that carry it away. And as you get further and further down away from industry and major, downtown and into residential areas, now your arteries are smaller and smaller. Think capillaries, right? So anywhere that you have a rupture along the way, now you have a problem with the circulation in this overall body that we're talking about. And we have thousands of restaurants and businesses that are all tapped into this and have the potential to have something go wrong in their treatment process or their backflow protection that could impart contaminants. So there is a lot more going on at any water utility than just treating water and putting it in the pipe. We need to shepherd it all the way to the end user. Maintenance is all part of this as well. So, and I'll talk about this at the tail end of this, but I wanted to give you a really good idea of the universe of jobs and skills and backgrounds that it really takes to provide safe drinking water, to study our natural waters, to treat wastewater effectively. And there's only about a couple of dozen different types of jobs and careers that somebody with GIS skills could immediately plug in and be a huge part of a successful team. Water system maintenance, asset management programs, knowing exactly where your infrastructure assets are. Obviously, it's not just mapping. There's a ton of information resident in those files. Date of install, materials of construction, any sort of other thing like that. And so that's all about turning data into information so that folks can do their jobs more effectively. Now, I said from source to tap and back again, the wastewater treatment process, and I already alluded to the removal of phosphorus as being a key concern in the US. Corrosion control on the drinking water side, one of the things that's really as science has advanced that we're really starting to key on is the use of phosphorus to sequester lead. If you were to go back into the early 1900s, there were a lot of cities in the US that not only used lead preferentially, some of them by ordinance required it. And if you ever stop to think about the origin of the word plumber, the Latin word for lead is plumbum. So it really comes out of what lead, and that's the reason that plumbers like to use lead. It's easy to bend. It doesn't kink like copper. And so it wasn't anything about health. It was easy to work with and it didn't leak. And so it was used an awful lot. So, GIS wasn't a thing back in the early 1900s, but as we update our asset inventories and where stuff is and what stuff is, converting those old analog or index card or post-it note type records into GIS inventories of assets is a more than a quantum leap forward for these systems and being able to protect public health. And then the wastewater treatment processes, they have to work in concert with the drinking water utilities in the town, because certainly whatever drinking water treatment facilities are putting into the water, that's something that wastewater plants need to know about. They ultimately have permits to meet before discharging back to natural waters of the state. And that varies depending on what part of the country that you're in. We're in a pretty environmentally conscious part of the country here. I did my doctoral work in Reno, Nevada, and Lake Tahoe is right there, and probably about as environmentally conscious a part of the country as you could find. And so you tend to have tighter wastewater discharge limitations in those parts of the country, maybe than you might have, say, even along the Mississippi River, where they lean on dilution being the solution to pollution in that part of the country a little bit more. So I'll do a light speed overview of partnership programs, because I want to give us plenty of time to talk about GIS and then have some discussion at the end. So all the stuff that we've been talking about over this last 30 or 40 minutes, the partnership programs that I manage, the continuous improvement and optimization programs, help utilities to look at their treatment processes, to look at their distribution management processes, to assess, are we doing, how do we measure up against industry standards? Are we going above and beyond regulations? We aspire to do more than meet a 0.3 NTU turbidity standard. We like to see our systems be at 0.1 NTU or less, because that is a much superior water that is much more protective of public health. And I can't remember, I apologize, but there may be a slide in here about what was the kind of the genesis event for the partnership. But back in 1993, the city of Milwaukee had a waterborne disease outbreak. It was cryptosporidiosis. And at the time, the drinking water plant was in compliance with the regulations. But the regulations and the science had not caught up with cryptosporidium and giardia as potential pathogens of concern. So they were meeting their NTU requirements, but the outcome was the science hadn't caught up. They were just meeting the compliance standards. They had cryptosporidium oocysts make it through their process, and 400,000 people got sick. The entire city of Milwaukee got sick. You could just Google Milwaukee crypto incident, and you'll get tons of hits on it. Somewhere between 50 and 100 people died during that event. It was directly attributable to the waterborne disease outbreak. Typically folks that were immunocompromised for one reason or another, whether it was, they were organ transplant recipients, or there are any number of reasons why folks might have compromised immune systems and they're more vulnerable to a much more severe version of the illness. So that was the driving force for, hey, we need to create this program of folks that really are driven to go above and beyond the minimum requirements and compliance. And that's the essence of what these optimization programs are all about, is we're not complacent with just complying. We are trying to relentlessly protect public health and do the very best we can with all of these efforts. So we look at, and I'll go through these very quickly because we need to talk about quite a bit more here on GIS and the application of it to these fields. But you can see the multiple barrier approach for turbidity reduction when we try to have our partnership utilities aspire to be less than 0.1 NTU with their finished waters. Distribution program, I've already talked about all the different challenges, an overview of all the challenges and priorities. And we asked them to look at all sorts of considerations. How well do they maintain residual? Do they have a main replacement program? Do they maintain their tanks? Do they clean and inspect their tanks with some routine frequency so that they're not impacting water quality? What about their backflow and cross connection prevention and control programs? And it's, all of those things force them to take a deeper dive into, are they really doing the best that they can to protect public health, or are they just striving to comply with the minimum regulations? We already talked about the turbidity guidelines. So right now, if you were to look at the surface water treatment rule, an absolute slam dunk, you have broken the rules, would be 1 NTU. But further than that, what the surface water rule requires is that utilities be 0.3 NTU or less 95% or more of the time. In our program, and you see in the bar to the far right, we ask utilities to strive to be at 0.1 NTU or less more than 95% of the time. And you'll recall that comparison of the microscopic slides from just a little bit earlier. So, and actually our excellence plants that we have, which is the very highest level of performance in our program, are at 0.04 NTU, 99% or more of the time. What they have found over time is this commitment to continuous improvement is they can always find ways to do just a little bit better and improve on their efforts to protect public health. And then we also have the Partnership for Clean Water, which is wastewater treatment and optimization, energy usage and optimization program as well. It's the newest of the programs, but we have about 120 wastewater facilities around the country that are part of this. All in all, the partnership programs and the facilities that are part of them serve about 140 million people on a daily basis in the United States. So, a little bit more than a third of the country is impacted by, this adherence to these optimization principles. I think you guys understand why we would want to optimize wastewater treatment plants. We talked about reducing nutrient loading out there, which can certainly decrease harmful algal bloom issues, eutrophication issues. Wastewater treatment's hugely energy intensive as well. So there's an opportunity to do the most good with economically by further optimizing operations. So We try to go above and beyond regulations. We certainly want to be tenacious and avoid complacency. We don't want to just comply. We want to do the very best we can, since we're in the business of protecting public health. And then this third out to the right really kind of gets to the core of what my understanding of what GIS is all about is we want to turn data into information. We want to have data-driven, informed decisions as much as we can. That's how we end up being being optimized, being as good as we can be at protecting public health. So these programs change utility culture. It's not that they can, they do, absolutely. There are programs that have, utilities that have been in these programs for 25 years, and they continue to find ways to get better and better over time. All right, so I made you all sit through all that. Let's talk about some GI science and technology in the water industry. So you get it. I am all in for drinking water treatment and environmental stewardship. We want to protect public health and the environment, but how does, and I'll say GIS, please forgive me, but I'm so used to referring to it that way. How does that fit in? Any number of ways, okay? And this is just a smattering. We've got technicians and analysts, we've got environmental scientists that are out there collecting information about stream flows and natural water quality, geospatial engineers, water resource engineers. The folks that I've had in my laboratory, years ago, I had to do a study for the Oklahoma City distribution system, and we really wanted to look at how disinfectant residuals and different chemical constituents varied around town in relation to the treatment plants, population centers. And that's a lot of data tables, but what we did was we stole a page out of the weatherman's book, and we did a bunch of color-coded maps to turn all of that data into information that people could absorb very, very quickly. Now, I'm sure that I'm grossly oversimplifying what the program entails, but from an end user, I cannot begin to express to you how valuable it is to be able to do that and take a bunch of folks that maybe are passingly familiar with why nitrification is an issue or decay of chlorine residual, and to express that to them with these sorts of maps and figures that's turning all of that complex data into information is beyond invaluable. So water utility data collection. So over the last 15 years or so, utilities have continued to migrate towards turning all of this, the data being tied in somehow to a geographic location, whether we're talking about where our source waters, lakes, streams, reservoirs, all of that. Once you get on the finished water side, it gets even more complicated, where the pipes and valves and pumps and, in all sorts of information, the material of construction, the date of install, and specific data elements and attributes. And so it continues to be leveraged more and more by both water and wastewater and consulting firms to turn data into information. So it's much more commonly used at water utilities now than it was by a long shot at the start of my career. One of the things that I'm seeing in just a very quick analogy to laboratory operations. So in labs, there's a ton of data being collected, microbiological data, physical data like turbidity and temperature and stream flow, chemical data. But turning all that stuff into something you can make sense of is a challenge. And a lot of chemists and biologists are great at collecting data, but this other side of it, how do you do that? How do you manage it? Well, what typically happened over time is, we would put that into what we call a LIMS, a lab information management system, because we're reporting primarily for compliance purposes, but I've always been a researcher. So we're doing all sorts of stuff about natural waters. And if we were to change this in our operation, how much more good would it do? So our LIMS people in the laboratories tended to be that chemist or biologist that, as a hobby, they love computers. And they said, well, I'll take a look at that. And they'd start to, they'd take us as far as they could. And some of those folks are really talented. And why tell you that story? That's the way a lot of GIS departments have sprung up at utilities. You have an engineer or a technician or a scientist that I'm sorry to, to be this informal, but they like computers. They go, well, why don't you go take a look at this GIS stuff? At City Utilities in Springfield, Missouri, the third largest utility in the state of Missouri, that's the way their engineering GIS department started more than a decade ago. They had an engineer that really had an affinity for just more than installing the latest software. And they pretty much said, go take a look at this GIS stuff. He just retired last year now in the department that had grown to about a dozen people. And was just critical, not only for water, but that's also a gas and electric utility. So they took that, what started out as kind of an afterthought, and let's put Phil over there on it because he knows a little bit about computers, to it grew into a full-fledged strategic concerted effort. So where you all come in now as people that have this background and training, that you want to be in that field. It's not just something you do as a sideline. And what I see is this next generation of maturity, the evolution of how can we get better and better about using these tools to do our jobs in an even more efficient and effective fashion. So we're seeing that maturation of the application of this field. And some utilities are way ahead of the curve, and some are still back in that, well, we've got, Joe or Jane that like computers, maybe we'll have them take a look at it. So there is a huge universe of opportunity to do good here in the protection of public health and in the environment. So smart water systems, this is something that we see more and more all the time. It's not just about how much water are folks using. I was just in touch with a colleague earlier today in Springfield, Missouri, that I worked very closely with. One of the things that we were doing there when I left and came to AWWA was system-wide installation of smart metering infrastructure for water, for gas, for electricity. We were able to, I should say since I'm at a different organization now, they were able to inform customers that they had leaks even before the customers knew, because of the AMI. In the smart system, it's not just saying how much water. It can detect whether they have high water usage at the wrong time of day, typically, which would be a leak. There's maybe a leak in their service line between their meter and their house that they don't even know about. Well, this all helps to make a smarter, more robust, more resilient system. So whether it's water quality and quantity at the source, the asset management, and the state of the infrastructure, and then there's all sorts of information that we collect about pressures and flows, turbidities, temperatures, chlorine residuals, all of that. There is a mountain of data that this technology helps us to turn into information to make informed decisions in support of the protection of public health. I love pictures. I love pictures way more than words, but and I'm only partially joking, because if you think about the mountain of information every night when you watch the weather forecast that you absorb in about 3 minutes of their time, that's what they're doing. They're turning all of this, the projected rainfall or temperature information, the high for the next day across the entire state, and they're turning that into a map that people can absorb very, very quickly. And I think that that's one of the things that is, for my money, is hugely, hugely important in the application of this. We see folks use it for the protection of water resources or natural resource management. We also see it on the finished side too, whether it's areas of high usage, areas that we've had to go fix the same main over and over, whatever the situation may be. For me as a water quality manager, it seems like we're going back to that same part of town with the same water quality issues. We need to take a deeper dive at the hydraulics of that area. Is it that the main materials are impacting it? Do we have a dead end in that area that we weren't aware of? And it allows you to go, wait a second, I was getting buried by all of the data. Now I clearly see that there's an issue over in this part of town, and we need to go investigate this. So it absolutely helps us do a better job in fulfilling our mission of environmental stewardship and public health protection. We can even dial down here, and it may be a little bit hard to see, but this is One of our utilities, they use this and they tie in into all these different locations, water quality data, and they have triggers set in there that if it falls outside their specified range, it flags them. Hey, take a look at this. Again, it's turning this enormous amount of data into information that people can absorb and act on. And so it can raise flags for areas of concern much more quickly than somebody looking at spreadsheets or poring over pages and pages of data would be able to typically. So Central Arkansas Water, and this is a partnership utility. And I apologize, I'm not intimately familiar with the slides here, but I know the people at Central Arkansas. I've known the person over this program for a long time. They're the largest water utility in all of Arkansas, serve about nearly 500,000 people, 2,500 miles of pipe. And I know they're kind of the poster child for a utility in starting to really come into its own with leveraging GIS and technology. So 3 water plants, 2 water reservoirs, a total watershed area of 115,000 plus acres. And you can see they use the GIS information to assess watershed landscape, and they use it for informed decision making, right? And so I would say these folks are well ahead of the curve of most utilities. And this would be, for a lot of the utilities I know, to follow their blueprint and learn from them would be a wise endeavor. They use it for all sorts of things, whether it's where their vehicles are and routing them for the most efficient workflows. That 2,500 miles of pipe, I don't know the exact number of hydrants, but I'm guessing they probably have between 10 and 15,000 fire hydrants. Now, fire hydrants are hugely important for a water system, for fire protection, obviously, but we use them for water quality management. And you have to get out there, and any system should be touching those and inspecting those on an annual basis to the extent possible. You have to really be certain that that thing's going to work when you need it to. Otherwise, structures burn to the ground. Hydraulic modeling, asset management, a lot of things that we've already talked about throughout the first part of this presentation. Watershed, source water management, billing and customer service information. Is there a difference in usage patterns that might help us detect whether or not there's a leak occurring in an area or at a residence? All of that sort of stuff is what Central Arkansas Water is, applying, their GIS and technology to. And so they have found any number of ways to just get better and better. They've even used it during the pandemic. And so declaring water as an essential need to citizens, obviously washing hands, people need water to drink. But one of the things you might have also heard about, in some of the reporting, especially down in Texas, and maybe your average citizen doesn't think about, but there are a lot of folks that they have to have water, more so than just the folks on the call today. They may have some medical need. There are people that need electricity at their house because they may have an oxygen pump that they have to have on for COPD or any number of things. And so this is another layer of information about their customer base to say, well, everybody needs water, but some of these, it is even more pressing matter of life and death to them. So what about their, in the future, what are some of the things they want to use it for, working smarter, not harder, whether it's for upgrades or maybe having more information at the fingertips of field personnel, outage notifications. If they have a planned outage or an unplanned outage, they can send out notifications by text or by call or email if they have that information for the customer. So that they, the sooner they can get word to the customers, the more responsive they're being to their needs. As far as mobile applications, I can tell you that the Aurora Water Department, their folks, they have a secure mobile GIS package where it's a smartphone, so it's not the same as a laptop, obviously, but they can look at pressures, they can look at segments of pipe, they can look at all sorts of information wherever they have a cell signal, and they're very, very proud of it. It's something, actually, the person that's over that with somebody in their distribution department that had an affinity for computers. And 20 years ago, they said, why don't you work on this? And he's still there 20 years later. He's just continued to learn and find new ways and innovative ways to leverage the technology for making sure their distribution system's doing what it should. Another example, Denver Water. I talked about lead service lines and the need to get lead out of the system. There's really no safe level of lead, according to CDC and EPA, especially for young, kids typically under the age of 5 or so, and in those developmental stages, it's particularly a concern. And utilities nationwide need to figure out where their lead service lines are, where infrastructure containing lead is, and like I alluded to earlier, some of that stuff is somewhere between 75 and 100 years old, and the records may not even exist anymore. And so as they've been able to go back through and take these old analog records, index card records, or any of that, they've started to translate all of that information into their GIS now, so that they've gone through their discovery phase, their detective phase. They're putting all that into the 21st century now, so that they can make more and more informed decisions, and they're going to go get the lead out of the system. And so that's an example right here that's probably impacting some of the folks on the call today. They just may not know that they have a lead service line. So they've identified this. There's somewhere, they originally thought they were around 85,000 or so lead service lines. Through this detective story and going back and putting all this into ArcGIS, comparing against construction permits and handwritten records, they realized that they're about 20,000 below that. They're in the range of about 64,000. They still need to get all of those out, but this will represent a total savings of around $50 million in that effort. That's what those additional 20,000 or so lines that they thought they had before leveraging GIS capabilities, would have amounted to an extra $50 million in expense. So what about AWWA? Just a flavor of some of the sort of things. You can see the M32 manual over there on the right, computer modeling of water distribution systems, hydraulic modeling, and GIS. It continues to be something that, even though we're probably a decade and a half into this awakening, I'll say, I think we really have just, as an industry in water and wastewater, we're really just beginning to scratch the surface. So it's great to be able to talk with you all today about what I see and how it's applied now, in kind of the dreamer in me seeing the kind of limitless potential. And then you all go, well, you don't even know the half of it. There's a ton of stuff you didn't even mention that's going on. And so that's why staying plugged into the academic community has always been a big priority for me. So what about careers? And I mentioned a half a dozen or so. There are tons more of types of careers within water and wastewater. Even, like at Central Arkansas Water, they have a GIS department now that's strictly dedicated to the application of this across all of their many efforts that we talked about. But, within engineering departments, the folks that are out there collecting data in the field on natural sources, in research endeavors too. I've done a lot of research throughout my career. We did a big study on some of the lakes in Springfield, Missouri, that were source water for the city. We took a look at nutrient variability throughout the lakes. We took a look at densities of blue-green algae throughout. We looked at several different water quality parameters, and then we used our GIS folks to help us create a lot of different figures that really showed how variable water quality was. We looked at it at different times and seasons as well, and to show the variability and how critical it was to be really trying to prevent any sort of development and man-made impacts around the lakes. We didn't want housing developments or hotels going up there, because it was inevitable that it would degrade water quality and create more challenges for the drinking water treatment over time. So there are literally dozens of careers that someone could find to contribute with this skill set within the water and wastewater industry. And I really haven't, even for the hour and 5 minutes or so that I've been talking, I still have barely scratched the surface on this. But with that, I would go ahead and I think I can stop sharing. And I'm more than happy to try to answer any questions, or we just have a conversation and you guys educate me on all the stuff that I missed or got wrong in that.
Oh, that was fantastic. I please, I need your slides for Monday. We're just covering the smart cities, the Internet of Things, and mobile GIS, and these things you mentioned. Please, send us. Please,
I'll send them to you just as soon as I get off the call here, Rafi.
I'm going to hack them and put them on mine. Excellent. Thank you, Todd. So I have several questions, but I will open it to, please, you guys have priority. Any questions or comments at this point? Peter, please.
First of all, I just want to clarify, is this recording going to be, is the recording of this meeting going to be available somewhere? I heard people talking about that.
Yes, I'll send a link on Monday.
Okay, because I'm going to use the GIS part of it for my mapping class for sure. This might be a little bit off of the main topic, but I'm just really curious, if the whole process and this kind of series of barriers you spoke about earlier in the presentation, how dealing with recycled water, is it distinguishable? I mean, is there a different process for recycled water?
There is. That's a great question, by the way. Thanks for it. I don't always say that. I know folks by reflex. Thanks for the question. That is a great question. Actually, within our partnership for clean water, that's something we're really looking at, the regulatory drivers for reuse. Certainly, we all live downstream from someone, right? The Aurora Water Utility has some reuse water as part of their portfolio of sources. They have some more pristine sources, but they've got some reuse water. And so it's certainly a consideration. And I'd say that there are places around the country that are doing it already. But the regulatory community is, that's whether it's on the wastewater side, certainly there's plenty on the drinking water side too. But I think that there's a lot of room for increased collaboration because we're really all in this together, and so just a real good example is Denver Water. They fought putting phosphorus in as a corrosion control, not because they didn't want to try to do a better job of controlling corrosion. They knew what an absolute nightmare it was going to be for the wastewater facilities in town. Now, phosphorus isn't that esoteric compound or contaminant that I think of when I think about reuse. There are tons of other things, but it absolutely is a consideration. And I can, I don't know if this is something you all would be interested in, but the advanced water treatment superintendent out at Aurora is a close friend and colleague of mine. They've got that Prairie Waters project out there that has some impacted waters that are reuse waters. They've done some research with Boulder, Scott Summers' group up there, and they've looked at a whole host of things that might be present in their source waters for treatment, whether it's pharmaceutical or personal care type of things, these things that traditional wastewater processes were never designed to remove. So it is a consideration. It continues to be an area of close inspection, and it's a topic for the continued evolution of the optimization programs. Is how does this fit in? We want it to be collaborative and not just all on one side or the other. The best solution is all of us trying to figure out how best, because it really is a vital water source, reuse water in a lot of parts of the country. It only makes sense if we can get a good handle on it so that we're doing the right things to protect public health.
Yeah, I just want to say, I suspect that eventually we're going to, with pharmaceuticals and that kind of thing, as we see these things show, endocrine disruptors or whatever, the experience of working on recycled water might pay off later down the line. I have a feeling.
I share that feeling.
Yeah. And yeah, and I will, on the chat, I saw the request by some of the faculty to share the slides also for their classes. So yeah, I will email it to the faculty list so you can have them. Okay, go ahead. Any other questions or comments at this point? Brian, please.
Hey Todd, thanks again for the great presentation. I just finished a section on water and water quality with an undergraduate class, and this information would have been really handy, and we'll come back around to it. So thank you. It's amazing material. I had a quick question. In thinking about the use of GIS, and I think you mentioned at one point in your slides about sharing information with stakeholders. I wonder if AWWA has any sort of citizen science sort of projects where they're engaging members of the public to maybe not just think about water quality, but maybe gather data that could be used by the engineers and the folks at AWWA to address some of these issues.
So AWWA specifically, I'll have to do a little bit of checking. It is a great idea. It's a matter of fact, it's something that actually is in place in several parts around the country. Some of the regulatory agencies have even, when they have folks that are invested, they want to learn how to do this, and they, like you said, citizen scientists that really are committed to trying to help. What an awesome blessing to have these folks that want to come in and help you and contribute for the greater good. So whether it's, I know in Northwest Arkansas, they have a Secchi Depth Day where they teach folks how to, which is a clarity of the lake. And there's some other things that they don't have to have a huge outlay of capital to give folks the resources they need to go collect, measurements that are worth basing some sort of decisions on. So there's a framework for that sort of thing out there. I think Project WET is one of the names that where you have this kind of, folks that are very, very passionate about wanting to help with this, and there's an avenue. But I will do some checking. I'll make a note, because they're, at the very least, what I would expect is, AWWA has, there are probably 250 or so different committees that, by the way, if any of the students or academics, professors joined AWWA, they have an opportunity to get on this committee and help move, whether it's on GIS or whether it's on water resources. There's a way to get plugged in there. And some of those committees may have some work that is centered around just the sort of concept that you're talking about. And I'll do some checking.
Very cool, thanks. I'm also, part of what I do is educational outreach. And so these are great opportunities to get community members involved. And like you said, not necessarily to make decisions per se, but to understand how data is gathered and where that could be used. I think that's really amazing as well. So thank you. Great applications. I'm learning a lot. So appreciate it.
Well, thanks for that. I appreciate the kind words. As far as the one slide I had that said how water works. So I had just finished, probably 3 or 4 months ago. We're doing some grant work that's really geared towards small systems, because there's a really pressing need across communities that serve 10,000 or less for upping their game, whether it's infrastructure renewal, understanding the sort of issues they have with treatment. So one of the things that we put together is an informational packet, a workbook. It looks like a comic book, but it's called How Water Works. And it basically takes us all the way from source to the tap, through wastewater treatment and back again. And it's anywhere from somebody that's in 4th, 5th, 6th grade all the way up to an adult. It's like, okay, I get that there's a whole lot more detail available here, but I understand why it's as complex as it is. I understand why it's expensive in time and in money. And so we have things like that that are available. I love talking about it. I think you guys can tell that I'm always, that's why I've always taught on the side, is I love the opportunity to learn and educate folks at the same time about how important all this is, because I do think most of the US tends to take it for granted, because the water's almost always there when they turn the tap on.
Tom, please.
Yeah, so I'll share all the similar sentiments about, an amazing presentation, and thank you for all the information. You touched on a topic that I was just about to ask a question about there, actually, having to do with small providers. So those that serve communities of 5,000-10,000 people or so. Some of your last slides there really kind of touched on all of the amazing technology things that we can do in places that have the resources to do those things, right? And of course, some of these small providers are perhaps in servicing communities that perhaps don't have the resources to provide the types of technologies that we need to have all the wonderful things that you talked about there towards the end with the GIS technologies and such. So I'm curious about maybe just kind of any general thoughts or sentiments about the barrier of entry to some of the technologies that you talked about, particularly on the GIS side, and how to minimize some of those barriers of entry for smaller communities, whether they be like mountain communities or here in Colorado or rural communities in Midwestern states, et cetera. So.
Sure. Another great question. So interestingly, about a year and a half ago at AWWA, I broadened my role. Instead of the optimization programs, which is my passion and what I came here for, I now the grants in the education and utility programs. The grants piece of that, most of the grants that we are delivering on currently are focused on small systems, 10,000 or less as EPA defines them, or USDA, the U.S. Department of Agriculture, has their Rural Utility Service, Rural Development Wing. USDA has 29 agencies, but this is a niche where they really are trying to provide funds to small systems that don't want to raise rates. It's a thing of pride. I haven't raised rates in years. It's like, what you're actually doing is you're sticking the next generation with the bill, because that stuff's got to be fixed. So if you're not doing it now, somebody's going to pay for it later, type of a thing. And so one of the barriers to entry, I wish I had all of the answers to that question, because we have a lot of great technical resources, but if nobody wants to listen, that's part of it. If they have a resistance to asking for help, I think so. There's some real social questions that I'm all ears for answers. A lot of times, most times at small systems, you hear that old cliche about folks wear a lot of hats. They might now, somebody like Estes Park, that's, they're less than 10,000, but that's a very robust small system, versus like maybe an Alamosa that had a waterborne disease issue more than a decade ago, or literally tens of thousands of small towns all across America that maybe they're only 1,500 people they're serving, and there's, hey, there's only 2 of us working here, so you can't go on vacation next week because I am type of stuff. And they're the manager, and they're the team leader and the team. So I think some of those things are very real barriers to entry for the technology. The problem is, it's like, we can't afford to pay attention. It's like, actually, you can't afford not to pay attention to this. This is the life raft that could help you really focus on the most important things. And a lot of this, it's not just on autopilot, but it is a way for you to focus on the things that only you can do, and let the system and the technology support you in that end. So to me, the barriers to entry tend to be a lot more the human factor, kind of the social, the resistance to it, than it is how complicated it is or anything like that. That's one of our issues that we find with delivering on our grants for small systems is not the content. It's even when it's free and you feed them, and by the way, you get continuing ed for your licensure, it's still a struggle to get folks there. And I think some of that is we're too busy. Some of it is, I don't want to cut time out of my schedule to come listen to you guys talk to me about something that then I'd have to go do something about, so it's complicated. But I'm pretty bullheaded. I think it's something that when you know, there are over 50,000 public water systems in the US. Something like 98% of them or so are systems of the size that we're talking about. So even though Denver serves, you know, a couple of a million people, Metropolitan Water District of Southern California serves 20 million people. There are tens of thousands of systems out there that 500, 1,000, 2,000 people, you have to really be worried about, are they getting water that is protective of their health? And that's where this technology can really help us move into, you know, the next generation forward. And that's what I'm very hopeful of.
Yeah, thank you for those comments. And it almost seems like an opportunity to kind of, like you mentioned, the next generation, kind of an opportunity to almost kind of leverage an interest in technology in this generation towards kind of perhaps improving the water quality situation in, like you said, the vast majority of our systems around the country. So yeah, interesting. Yeah, really cool.
Absolutely. You know, and we might be lucky. You and I might take a drive out into the mountains and we might find somebody running a water system that's not so different from you or I. They decided they wanted to retire to a small town, and I'll run your water system. You're like, holy cow, you know this stuff backwards and forwards. But for every one of those that you find, we're probably going to find several hundred that folks don't know what a milligram per liter or a part per million is. And it's like, but you're the one over the water system in this town, you know? And so I chalk it up to their folks that are trying to do the best job that they can, but that's a scary situation about where we're at in those, all of those small communities across America. There's a lot of good to be done. So, you know, even though I talked an awful lot the last hour and a half, the students that are on the line, the work is barely just beginning. There are several lifetimes of good work to be done here in this area for sure.
Excellent. Matt Cohen, do you have your hand raised, or I don't trying to ignore you?
Yes, I raised it.
Okay, go for it.
All right, thank you. Hey, Dr. Brewer, this is Matt Cohen. Thanks for the talk. Really interesting. I'm doing a water systems focus in my program right now, so I'm really interested to learn about some of the concepts that you were talking about. But I was hoping you could touch on what capacity or what role that you're aware of that water treatment facilities and operators have in tracking communicable health concerns such as viruses that you touched on earlier. Did these utilities or operators have any role in tracking COVID-19 through water infrastructure?
Generally, no. But there are certainly utility, and I know that there were some efforts around the country for sure looking at wastewater streams as a comparison to see, are we really doing enough testing in this community? Because we're not getting very many positives, but we're sure finding it in the wastewater streams, which is probably, if not an indictment, it's at least an indicator that their testing efforts need to be bolstered, which was the case in a lot of the country. So expressly as a requirement or part of their everyday jobs, even in normal times outside of COVID, not typically, no. Now, what there is in place though, between like the county and state health agencies is a network. If, for example, so going back to the Milwaukee crypto outbreak in, in 93, or even the E. coli outbreak in Walkerton, Ontario in Canada in 2000, which was a town of about 7,000, 5,000 people got sick, 7 people died, type of a thing. The surveillance was not in place and effective there. What ended up happening was the way that they found out that people were sick, literally in Milwaukee, one of the doctors in town got sick and he went to the pharmacy to find some Pepto-Bismol and he couldn't find any anywhere. So why is this stuff not anywhere? And they said, it's not a supply issue. This stuff's flying off the shelves. Well, that's weird, and so they started. And so you want to talk about really falling backwards into finding out something bad is going on. In Walkerton, Ontario, the same thing. As a small town doctor. Luckily there weren't very many doctors in town, and he he's like, wait a second, holy cow, has there been a bad, salad bar in town or something? Everybody's sick. And they started backtracking through. So what we've done over time in our industry is that whether it's the hospitals in the emergency rooms or these agencies, they report those communicable diseases or these types of outbreak activities. They have very, very low thresholds to report them, back like to the county authorities or the state authorities. And there are triggers to say, okay, by the way, hey, this is all happening over in Aurora. We need to contact the Aurora Water Department and see if they're aware of anything going on with their water treatment, or if they have any issues in their distribution system. It's interesting, Matt, if you were to look back, if you were to Google Dr. John Snow and the Broad Street pump incident, it kind of is at the very heart of modern epidemiology. Back in 1850s London, the Broad Street pump, there was a cholera outbreak. Now, this is before the germ theory of disease. This is before Coke and Pasteur by a good 25 years. So somebody talking about invisible tiny stuff in the water making you sick was more likely to be committed than they were to be listened to. So he did a bunch of research. He did a bunch of interviews. It was a little bit complicated back then because a lot of the folks, even in mid 1800s England, they'd have wait staff, house staff. So maybe the person that got sick wasn't the person that actually went to, it wasn't even a well, it was a cistern. And it had, in the Thames Rivers right there, this is back when, wastewater just went right out into the river and all of that. But he mapped all this out. And he was able to show that, the concentration of the death and disease is all around this Broad Street pump as a water source. And what the people wouldn't listen to him, what they ultimately did was they removed the handle on the pump for the cistern so people could not access the water anymore. And that, oddly enough, is credited as really the beginnings of modern epidemiology that now goes into just what you're talking about is, hey, we've got an uptick in this, we need to not just write that off. We need to see if we can track that back to the source and see if it's something, more broader reaching. Now with COVID, the issue for water and wastewater utilities really was more focused around, are our folks that are supposed to be manning these facilities going to be able to show up for work, or are they sick too? There are a lot of utilities that were looking at, not a lot, but there were some of the more progressive ones looking at housing operators in place and keeping them sequestered from the community to minimize exposure so that they could continue to provide these critical services. But as far as a direct link to, a health agency and reporting, they would really be more the recipients. It's not something that they would have been testing directly. They would have been working with folks that would have been collecting samples and then sharing that information back to them. The indications are that at least in drinking water and in general that, any of the handful of disinfectants that are used in drinking water treatment are pretty effective against the virus. So there wasn't, and after the initial stages and the fear about what about drinking water, they quelled those with some science pretty quickly to say the multiple barrier treatment concept does a pretty good job of removing any kind of risk for coronavirus. And there's been there are dozens of different types of biological contaminants that have been studied over time for disinfection efficacy. So hopefully I answered your question somewhat there.
Yes, thank you very much.
All right, perfect. We're right on time, but I'm gonna abuse everybody's time for just 1 minute. Okay, 1 minute. There is, with all this availability of information, the GIS and everything you mentioned, what is, from your perspective and your experience, the issue of security in terms of, not to give any ideas, but people can poison the water sources with very high effective poisons. What is the concerns about security in general out there within the AWWA?
Security is a paramount concern. And it used to be, especially after 9/11, there was a huge push in the water industry, particularly, but wastewater as well, to really take a good look at physical security. Now, a lot of the water and wastewater facilities in the US for decades have had chlorine gas and maybe tons of chlorine gas at their facility, because the chlorine gas can then be used effectively. It's a lot cheaper than liquid chlorine. There are a lot of reasons for its use, and it's been used safely in the industry overwhelmingly. But it's also, it's kind of what mustard gas was all about in World War I. It is something that, I don't know about mass destruction, but if a 1-ton chlorine cylinder were to rupture and release, the liquid's going to turn into gas. It's going to expand 400-fold, and people don't do very well breathing that stuff. So it could absolutely be a weapon of some mass destruction, right? So there's a lot of concern after 9/11 that people that of whatever origin may want to break into these facilities and access tons of this material to do very, very bad things with it. So there was a big push for physical security that continues even today, whether it was to grab chlorine cylinders or other stuff that might do bad things out in the community, or to directly taint the water by introducing contaminants in there. Now, as far as source waters go, I always worry about it, but we do have the treatment process. We do have dilution. We have all sorts of things in our favor to make it, if you were really wanting to do harm to, a community, going to their source waters is not the smartest or most effective way to go about it by a long shot. Now, you leap forward to the last few years and even to the last 6 months or so, where we start to talk about cybersecurity. The SolarWinds thing last year, you guys may know more about that than I do, but there were tens of thousands of entities that were impacted, federal agencies, water utilities. So there's a huge concern about that. And some of you may have seen in the news here recently about it's a pretty small utility down in the Tampa area, Oldsmar, that had their system hacked into. And people changed some set points on some treatment parameters. Now, as soon as they did that, the system alarmed the operator on duty and said, wait a second, this value for this treatment chemical has been changed outside of specifications, and he was able to change it back. I know from firsthand knowledge of that system and people I work with that their system was not robust in any way. It was an old Windows 7 system with common passwords for remote access. So it's like the poster child of do not do this if you want to have a secure system. But between that, which is kind of the very, very low bar when you think about thousands upon thousands of very small systems that might think that's okay, to something as sophisticated as the SolarWinds hack, cybersecurity is a huge concern. And I'll go one further with you, Raphael. We do an annual survey out to the water industry, to a couple of thousand utilities and members and everything. It's called the State of the Water Industry Survey. And we asked them to rate several things as what their primary areas of concern, whether it's infrastructure, whether it's endocrine disruptors, whether it's any number of things. And there are several things in there on security. Interestingly, and I work with a guy out of our DC office that's over water reliability, cybersecurity, physical security. Some of the physical security, perimeter type security, sensing security for water quality integrity rated very highly, but cybersecurity was rated way down the list. And I said, just in where that stuff is rated tells me that there's a steep hill for us to climb in education, because they should be equating all those should all be not lumped together in terms of topics, but they should all be right there next to each other in terms of importance. Because now the new digital age, you're far more, you don't realize, but you're under assault on a daily basis in the cyber environment, so you better get up to speed or more bad things will happen. So it is very much of concern. It's something that we're actually getting ready to roll out about a dozen webinars on cybersecurity and really driving home that this is a much bigger issue than folks realize. That, you know, you might have been hacked, you might have gotten a phishing email that you clicked on and provided access into your system, and you don't even know it yet. And so we're on our way there. There are a lot more folks that need to wake up and smell the coffee, but it's hugely, hugely important. And we're trying at AWWA to make them hear the message.
Awesome, perfect. Well, again, thank you so much for your patience, and Todd, for your generosity with your time. Thank you everyone for coming. Todd, thank you so much again for an awesome presentation. We really appreciate it. And again, good to see you everyone. I'll send around the slides, and we'll make it to all the students also in some way, shape, or form. And we'll pass around where the recording is posted also, okay? Thank you for coming, guys.
Thanks, everyone.
Thanks, everyone. Have a great weekend now.
Thank
Thanks,
you.
everybody. See you.
Bye.